Hello everyone and welcome back. Today we will be starting chapter 3, which is on derivatives. By now most of you should have already gotten your limits test back. Don't feel too crestfallen if you didn't do nearly as well as you might have expected, because that's the hardest test of the year, I'll guarantee you that right now. But that's open to judgment, alright? So derivatives should help boost your grade, because once you understand the concepts and the techniques, it's just basic arithmetics, right? Alright, so let's begin by talking about the definition of a derivative. In section 2.4, we define the slope of a curve as of the curve y equals f of x at the point where x equals a to be m equals the limit as h approaches 0 of f of a plus some infinitesimal value h minus f of a, right? All of that divided by that really small value h. So when such limit exists, this limit is called the derivative of f at a, right? Now this is a completely new term, and I understand if you guys feel completely confused by this, but that's alright. So in this section, we investigate the derivative as a function derived from f by considering the limit at each point of the domain of f, right? So now into the formal definition of a derivative. A derivative of the function f with respect to the value of variable x is the function f prime whose value at x equals, so f prime equals the limit of h approaches 0 of x of f of x plus h, right, minus f of x over h, provided that the limit exists. So now you might be asking me, well, what's the difference between a derivative and slope? Once again, alphabets. No, I'm just kidding. There is no difference, right? Your slope is a derivative, right? So as I mentioned earlier, you have three types of functions. You have the position function, you have the velocity function, and you have the acceleration function. The slope gives your velocity, right? It tells you how fast you're changing per given unit of time. Your derivative tells you the exact same thing. So when you're learning calculus, try to incorporate, as I mentioned earlier, calculus is a very dynamic concept, so you need to be able to really link it with everything that you've learned thus far, right? And that's how you're going to be successful in calculus this year. So this is your derivative, and this is your derivative function, and just remember, derivative is slope, right? Slope up here, sorry. I didn't get that in the frame, but that's alright. So let's do an example here from the textbook. This is example 1 from chapter 3, section 1, right? And we're going to apply the definition of a derivative, right? And we are asked to differentiate, or that is find the derivative of the function f of x equals x cubed, right? Now the function f of x is simply the position function. It gives the position of x at any given value x, right? Now we're going to find the change of x, or in simpler term, slope, right? So what we're going to do is we're going to apply this definition, right? Or this, pick your poison, doesn't really matter, right? So we're going to write f prime of x, and it's f with a function of it's f of x with an apostrophe between the f and the x, right? That just shows you you're dealing with derivatives, equals the limit as h approaches 0 of f of x plus h minus f of x over h, right? And when you're doing homework, try to copy it once or twice, because you need to be able to get the thing stuck in your head, right? And so now we apply, now we make it case specific, and we do x plus h cubed minus x squared, all of that over h, right? And the reason why we cubed it was because the function, it was x cubed, right? And now you just do a bunch of boring algebra 2. So limit as h approaches 0, make it look like an h. Now you have x cubed plus 3x squared h plus 3x h squared plus h cubed, all of that minus x cubed, right? Divide by h. Your x cubed cancels out. You're left with a bunch of x's and h's, but you should also realize that all of them have x's, all of them have h's, right? Which means you can take them out, and you have limit as h approaches 0. I'm just going to do this in my head, so basically what you're going to do is you're going to cancel all the h's, right? this becomes second power, this just becomes first, right? And all of this just eventually becomes the limit as h approaches 0 of 3x squared plus 3xh plus x squared, right? And this equals 3x squared, because the h's all just turn to 0 and fly away, right? So that's your derivative at, so that's the derivative of the function f of x equals x to the third. You just completed your first differentiation if you were following along, or you just saw your first differentiation if you didn't pay attention in class, okay? Alright, so there's an alternate definition for derivative at a point, and that definition is for the function f, right, f of x, at any point x equals a, right? Your derivative is given by f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. And what you're looking at right here is basically exactly the same as this and as this, right? What you're doing is you're taking your new function, or your new function, and you're subtracting it by the original one, and you're also dividing it by the displacement, which is the exact same thing as doing delta y over delta x, right? So now I'm going to move on and do a slightly different question, and we're going to apply the definition that we just learned right here, right? So we're asked to differentiate f of x equals the square root of x, right? At the point x equals a, right? What we're going to do is we're going to use this function right up here equals the limit as x approaches a, right, of f of x minus f of a, and this is an x, by the way. My handwriting is usually not this sloppy, but I am sorry, it is. I apologize for my handwriting right now, but I guess it's legible. So now you plug in what you have. So now your f of x just becomes the square root of x, right? And your f of a becomes the square root of a. Your bottom still remains the same. Okay, so now what do? Now you rationalize. If you still remember what that means from Algebra 2, that means you multiply by like the reciprocal from the top, and you try to get rid of all your radicals, right? Because radicals are radical, and you don't want them. So you simply multiply, right, like this. And I know this isn't standard notation, but I'm just doing this all in one step since this is a tutorial, right? And now you get limit as x approaches a of x minus a, right? A plus b, a minus b, and you get left with a squared minus b squared, right? And on the bottom, you get x minus a times root x plus root a, right? Now, this is pretty conspicuous. You just cross it out, and now you have the limit as x approaches a of basically 1 over root x plus root a, right? And as your x approaches a, your limit as x approaches a, you actually end up, or here I shouldn't write the limit, but just know that as your x approaches a, this becomes root a too. So now you're left with 2 root a, and thus when you derive f of x equals root x, your derivative ends up looking like this. Okay? This means that at any point a, right, the change in position of the function, the square root of x, is modeled by the function 1 over 2 root a. Okay? That's all there is to know. There's also notation that I want to go over for derivatives, because you will go through. I mean, Mr. Wilson, I'm pretty sure, has done a wonderful job of explaining the notation and which ones to show if you're diligent calculus students, or which ones to use if you're being sloppy. But there are 4, right? So the first one is the one that I've been using all along. It's pronounced y prime, right? Or it could be anything prime. It could be a prime, d prime, f prime, anything, right? And it's nice and brief, but it does not have an independent variable, right? So sometimes you're deriving was according to x. Sometimes when you're doing vectors, you don't know what that is yet, but sometimes when you're doing it, according to another variable, this doesn't really do a nice job of showing you what the independent variable is, right? Now the next one is dy dx, and this is pronounced exactly how it's written, dy dx, right? And it names both the variable and uses d for derivative, right? So derivative of y over dx. This is delta y, delta x, slope. And you can also use d over d dx of f of x. This is what I used basically for my first 2 weeks of derivatives until I figured out that you can use this, right? And it emphasizes the idea that differentiation is an operation performed on the function f of x, right? So now we're going to learn how to read graphs / graph derivative graphs, right? This will show up on the AP exam, so do pay attention to this next section, okay? And also, if you want to go into physics, especially AP physics, let it be, or it could be B or C, then your ability to read these graphs will need to be enforced, right? So let's begin by looking at the position graph. This is a position graph, right? The position graph is a fancier name for a graph that you would see on a calculator screen if you were to plug in a function directly into your calculator, right? Now, there are 6 points that I've picked, and oh, by the way, this is example 3 in your textbook. So if you want to follow along, just do that. Just go to example 3, right? And this discusses the behavior of f in terms of the signs and values of f prime, right? And so what we have done here is we have picked 6 points, A, B, C, D, E, and F, right? Yeah, that's 6. Okay, all right. And we have calculated the slope at each one of these, or at each of these 6 points, right? So at point A, your slope is 4. At point B, your slope is 1, right? If you were to draw a tangent line, it looks something like that. That's about 1, right? And then at C, it's 0. It's flat, right? D, -1. E, also -1. And F, 0, right? Okay, you're going to need to draw a lot of tangent lines to model this. But by plotting the slopes on the graph of f of x, you can obtain the graph of y prime, or f prime of x, okay? So let's begin. Now you still have your x-axis, right? This is still x, but now your y-axis has changed. Instead of showing y or position, you're showing y prime, or you're showing slope. You're showing change, right? So let's look at this. So when x equals 0, right, on this position graph, your slope was 4. Now don't look at the 1. The coordinate for a is 0, 1, but that's not what you would plug in here. Remember, your y-axis is now slope. So what is the slope at x equals 0? Well, it's 4, right? So a, you have a prime equal 4, right? So at x, it's 4. Next, you look at b, right? B at 1, right? B is at x equals 1. The slope of 1 over at b, the slope is 1, right? So at b, when you come over here at x equals 1, your slope has to be 1, right? It's not 4.5 or whatever, it's 1, right? At c, your slope is 0, right? Because it's a horizontal asymptote, right? Or it's just a horizontal line, right? Not an asymptote necessarily. It's a line, right? So your c prime at 2 would be 0. And you do the exact same thing for d, e, and f, right? At d, it would be -1, so -1. E, it's also at -1. And f is at 0, right? And you might be wondering why this little bit goes under -1. Well, it's because at any point in between, possibly here, the slope might not be -1. It might be less than -1. It might be like -1.2 or something, right? And that's why you have a little curve down here before it evens out, right? And so in order to be able to graph acceleration graphs, or not, excuse me, not acceleration graphs, but velocity graphs, you have to be able to figure out exactly. You have to figure out the slopes for a couple of lines, or for a couple of points, and then you have to be able to do this, right? You can't just expect to conceive of a graph in your head unless you're like a natural-born physicist, right? You have to be able to plot it, right? And this is how you're going to end up getting to your velocity graph.